Imagine a realm of monstrous tempests, fatal radiation fields, and absolutely mesmerizing grandeur. We are talking about a cosmic powerhouse possessing an existential mass so incredibly vast that it fundamentally alters the behavior of our Sun itself. Right now, Jupiter is rapidly transforming into one of the most intensively analysed targets across our entire astronomical neighbourhood, having been visited by 7 distinct flyby spacecraft, tracked by 2 dedicated orbiters, including one that continues to actively send back data as we speak, and with 2 more highly advanced voyages currently on the books. Humanity has an immense amount of ground to cover regarding the 5th planet out from our solar centre. What internal or external forces are truly responsible for giving this world its highly characteristic reddish tint? What unique materials actually make up its colossal bulk? What secrets are buried deep underneath those thick, visually impenetrable layers of swirling vapour? What do we genuinely understand about its legendary and enduring Great Red Spot? The truth is that Jupiter performs an absolutely indispensable function when it comes to shielding the rest of our cosmic neighbourhood, and the moment has finally arrived for us to dive directly into its greatest enigmas. I am Alex Milan, and you are tuning in to Astrum. I invite you to join me on this journey today as we break down absolutely everything you could ever possibly want to uncover regarding the giant world of Jupiter. Positioned out on the remote fringes of our main asteroid corridor, the 5th planet from our central star maintains its orbital path right between the domains of Mars and Saturn. It tracks a path that places it roughly 778 million kilometers away from the Sun on average, a distance that can also be expressed as 5.2 astronomical units, and it takes about 12 Earth years to finish a single round trip around the Sun. When you look at the planet's rotational tilt, you will find it is remarkably upright at a mere 3 degrees. Because of this near vertical orientation, the world experiences virtually no noticeable seasonal shifts as the year progresses, which stands in stark contrast to what we see on Earth or Mars, though it is quite comparable to the conditions found on Saturn. Furthermore, its physical dimension measured across the equatorial belt is significantly larger than the measurement taken from pole to pole. This is an incredibly gargantuan world, easily ranking as the absolute largest planet residing within our solar system. Its structural mass is so immensely overwhelming that it equates to roughly 1,000th the total mass of our Sun. At first mention, that fraction might not strike you as particularly mind-blowing, but the perspective changes completely the moment you understand that our Sun alone swallows up 86% of every ounce of matter within the entire solar system. Once you grasp that fact, you can see that Jupiter effectively comprises nearly the entire remaining balance of planetary material. Its overall mass is a staggering 2.5 times greater than the combined mass of every single other planet in our solar system put together. And this extreme concentration of matter gives rise to a truly fascinating physical anomaly. The common barycenter shared between Jupiter and the Sun does not actually reside inside the star. Instead, it is located out in open space completely above the solar surface, sitting at a distance of 1.68 solar radii from the absolute center of the Sun. Let us take a moment to really unpack how barycenters operate in the universe. Whenever we picture a smaller celestial object moving in an orbital path around a much larger one, our default assumption is usually that the smaller body exerts zero gravitational pull on its giant partner. We assume this simply because in the vast majority of normal cases, the reciprocal force is so incredibly tiny that it is practically unnoticeable, such as the International Space Station looping around the Earth, or even the planet Mercury charting its course around the Sun. Even so, that tiny gravitational tug is absolutely still happening behind the scenes. A barycenter is fundamentally defined as the shared center of mass existing between any 2 interacting celestial bodies, marking the exact spot in space that both objects are actively circling around. Because Jupiter possesses such a colossal mass and sits at such a significant distance from our central star, it behaves entirely differently than a small planet like Mercury. Its gravitational footprint is completely impossible to ignore. As Jupiter makes its massive rounds about the Sun, both bodies are locked in a continuous. Subtle orbital choreography around this shared centre of mass, which, as noted, hangs completely suspended above the actual physical surface of the Sun. Allow me to clarify this mechanical law by sharing a basic real-world demonstration. If I were to take a highly dense, heavy object along with a much lighter item and securely fasten them to opposite ends of a single long rod, we would have to locate the precise centre of mass to make the rod balance perfectly on a pivot. As you can clearly see in this setup, the balancing pivot point naturally winds up resting much closer to the heavier item on the rod. Now, if you simply visualise the heavy item as the Sun, the lighter item as Jupiter, and the balancing rod itself as the invisible bond of gravity, you will have a perfect mental map of exactly how a cosmic barycenter functions. Even though Jupiter undeniably commands the highest total mass of any planetary body in our local system, it does not actually claim the crown for being the most compact or dense. The only reason it holds the title of the most massive planet is due to its sheer immense volume. If the planet Neptune was somehow expanded to match the exact physical dimensions of Jupiter, Neptune would easily become the most massive body of the two. Conversely, if you were to shrink Jupiter down until it was the exact same size as the Earth, our own home planet would turn out to be more than 4 times more massive than the compressed gas giant. As things actually stand in reality, the total diameter of Jupiter stretches to an incredible 11 times the width of the Earth, and its overall structural mass calculates out to a massive 318 times greater than Earth's total mass. As we all well know from basic physics, an object's mass is what directly dictates its gravitational pull. This rule means that Jupiter generates an absolutely enormous gravitational field, which registers at more than double the strength of Earth's gravity, measuring an intense 2.528 Gs at its theoretical surface level. The sheer reach of Jupiter's gravity is so profoundly influential throughout our cosmic neighbourhood that it actively alters the behaviour of every single planet to some measurable degree. Its gravitational pull is powerful enough to completely rip passing asteroids to shreds, and it has successfully snared a minimum of 67 confirmed moons over time. In fact, a number of planetary scientists are convinced that Jupiter violently obliterated a vast multitude of early celestial bodies during the chaotic ancient history of our solar system, while also completely preventing entirely new planets from ever organising themselves in the first place. One highly specific and famous example of this ancient gravitational disruption can be seen in the asteroid known as 4 Vesta. Researchers even calculate that the overarching gravitational reach of Jupiter remains so incredibly potent across the solar system today that it is continuously shifting Mercury's already highly irregular orbital path. They predict that in a few billion years, this constant nudging might cause the tiny planet to either plummet directly into the Sun or be cast out of the solar system completely. At the present moment in time, however, the giant planet might actually be serving as the ultimate guardian angel for the 4 rocky inner worlds. If Jupiter were not out there constantly operating as a giant planetary vacuum cleaner, it would not be actively drawing in highly hazardous incoming objects like long-period comets. It would not be disrupting their trajectories enough to hand them a sudden boost of kinetic energy that flings them entirely out of our orbital neighbourhood. As we established, Jupiter is the 5th planet out from the Sun, situated roughly 5 times further away from our central star than the Earth is. Despite being located that far away, it still frequently manages to rank as the absolute 3rd most luminous object illuminating our night sky, trailing only behind the Moon and Venus. I really want to demonstrate to you just how brilliantly radiant this planet appears, using nothing more than a standard consumer video camera. We can capture Jupiter in the night sky with incredible ease. And because it can reach a peak apparent magnitude of 2.94, it is fully capable of casting distinct physical shadows on Earth. Because it stands out so vividly in the darkness, It represents an exceptionally popular and rewarding target for backyard stargazers, as consumer-grade telescopes have advanced dramatically over the past few years. It is truly mind-boggling to realise what kind of intricate planetary details you can now observe directly from your own back garden. Now, what is actually responsible for generating those iconic, world-spanning atmospheric patterns? The visible cloud layer itself is surprisingly shallow, measuring a mere 50 kilometers in total thickness, and it is largely composed of frozen ammonia crystals, which is quite similar to the atmospheric makeup found on Saturn. However, the brilliant coloration we see is caused by distinct chemical mixtures getting cooked up deep down within the intense interior of Jupiter and subsequently floating upward. These specific colour-producing compounds are technically referred to as chromophores. The moment they bubble up into the upper cloud decks, they begin to chemically react with the incoming ultraviolet radiation streaming from the Sun, which ultimately generates those magnificent, multi-hued atmospheric ribbons. This represents an incredibly dynamic ongoing cycle, meaning that the visual presentation of Jupiter can alter quite radically as time marches on. Even if the specific colour schemes of these bands undergo dramatic shifts, the actual latitudinal coordinates where these ribbons sit stay stable enough over time that scientists have assigned them specific standard names and designations. Even so, they can definitely expand or contract in total width over the passing years. A massive amount of localised storm activity and violent cross-current turbulence naturally erupts right where these opposing atmospheric bands rub against one another, and this violent friction serves as the primary driver and mechanical engine keeping Jupiter's legendary Great Red Spot spinning. This legendary tempest is absolutely gargantuan in scale, boasting physical dimensions that could easily swallow up the entire diameter of the Earth inside its borders. It has actively persisted for as long as humans have possessed the tools to look for it, tracking all the way back to its initial verified discovery during the 17th century. It could very well turn out to be a permanent structural attribute of the planet itself, though it is highly fascinating to note that the storm has actually been steadily shrinking in total size ever since astronomers first started keeping formal records of it. The underlying scientific explanation for its deeply intense reddish hue continues to be a mystery, and the overall coloration of the vortex can shift immensely over time, moving from a dark brick red tone all the way down to a nearly colourless white. The premier scientific hypothesis explaining its colour points to complex chemical compounds being systematically torn apart by solar ultraviolet light high in the sky, working through a process that is virtually identical to what occurs across the rest of the wider planet. This massive vortex actually sits significantly higher up within the broader atmosphere than the neighbouring cloud layers, and because of this elevated position, it is able to interact with raw, unblocked sunlight on a much larger scale. That altitude difference would perfectly explain why its localised colour signature can appear so much more vibrant and intense than any other feature in the surrounding area. However, Jupiter does not simply boast a single scientifically compelling atmospheric vortex. Another major storm system, which has been dubbed Red Spot Junior, initially organised itself when three smaller individual storms collided and fused into a single entity between the years 1998 and 2000. Up to this point in time, it has managed to sail right past its much larger neighbour completely unharmed, developing into a highly prominent feature on the planet's face. It could easily survive for another couple of centuries, provided it manages to avoid the destructive path experienced by a separate, similar storm system that wound up steering directly through the violent core of the Great Red Spot itself. So, what do planetary scientists believe Jupiter is actually constructed of beneath the surface? Well, much like the structural layout of Saturn, directly beneath the upper gaseous sky lies a transition into liquid hydrogen, followed by an even deeper layer of metallic hydrogen. The deeper down into the planet's interior you travel, the more incomprehensibly massive the surrounding pressure becomes, under these unimaginable states of crushing pressure. Hydrogen begins to shed its normal gas properties and behaves explicitly like a conductive metal, and resting underneath that metallic mantle lies a dense, frozen mixture of ice or an intensely compressed rocky core. Because we are completely unable to replicate the mind-boggling pressure environments of Jupiter's interior inside labs here on Earth. We do not truly understand what exact physical properties these deeply buried materials exhibit at the core level. According to current structural models, roughly 90% of Jupiter's total substance is believed to be hydrogen, with helium making up about 10%, alongside minor trace quantities of methane, ammonia, and various other elements. Jupiter spins at an incredibly high velocity, rotating faster than any single other planet in our solar neighbourhood, and finishing a full local day in a mere 10 hours. However, because the planet is not a solid mass of rock, it does not rotate at a uniform speed across its entire body. A full rotation completed at the polar regions takes roughly 5 minutes longer to conclude than a rotation measured at the equatorial belt. Back when I was a child, I remember being intensely curious about why Jupiter never managed to ignite into a full-blown star, especially when you consider how immensely massive it is, and the fact that it is overwhelmingly made out of highly flammable hydrogen gas. Surely, all it would take is for someone to cruise out there and toss a single lit match into the atmosphere to set the entire planet ablaze. Well, the disappointing news for my childhood imagination is that actual stars do not generate light and heat that way at all. Plus, there is virtually zero free oxygen present in Jupiter's atmosphere to support chemical combustion in the first place. Real stars generate their immense heat outputs via the process of nuclear fusion, which is sparked exclusively by the mind-boggling gravitational pressures, crushing down at the star's absolute core. Modern astronomical calculations indicate that Jupiter would need to be roughly 75 times more massive than it currently is to generate enough internal pressure to trigger fusion and become a star. Though it is highly interesting to note that its total physical volume is actually not that far off from the dimensions of the smallest known red dwarf stars in the universe. Furthermore, as you might have spotted in this specific imagery, Jupiter does indeed possess its very own system of rings. They are certainly nothing on the magnificent scale of Saturn's ring system, but there are 4 distinct planetary rings looping around the world. The primary main ring is exceptionally thin, but shows up as quite luminous, while the remaining structures are notably wide, but remain exceptionally dark and difficult to see. This primary ring stretches roughly 6,000 kilometers in total width, and the sole prominent feature you will easily call out within it is a specific structural gap known as the Metty Notch. Another critical characteristic to highlight regarding Jupiter is its profoundly powerful magnetosphere. It registers as a massive 14 times stronger than the magnetic field shielding the Earth, a force driven directly by the rapid spinning of the planet's liquid metallic hydrogen interior. This layout gives it the absolute most powerful magnetosphere of any planetary body operating in the solar system, a magnetic field strength that is surpassed only by the highly localized sunspots erupting on the Sun itself. There are a handful of distinct reasons why this immense field is so incredibly fascinating to researchers. First of all, these wide-reaching magnetospheres systematically catch the incoming solar wind and funnel those charged particles directly down into the planet's polar regions, which subsequently ignites truly magnificent, world-scale auroral displays. The second major reason is that the 4 largest moons orbiting Jupiter find themselves entirely shielded from the harsh solar wind because their paths reside safely inside this protective magnetic bubble. This layout implies that these individual moons do not actually need to generate their own independent, powerful magnetic shields, because Jupiter is already doing all that heavy lifting for them. However, this convenient arrangement does not mean these worlds are entirely safe from harm. Jupiter is surrounded by an incredibly intense, high-energy radiation belt, the very same destructive radiation corridor that has historically crippled or completely fried almost every single robotic space probe that has ever attempted to coast through it. The absolute closest large satellite orbiting the planet, the Moon Io, tracks a path that sends it directly through the most dangerous heart of this high-energy radiation corridor soaking up a staggering 3,600 rem of radiation every single day on its raw surface. To offer a clear point of comparison, any human being who found themselves unprotected and exposed to that extreme level of radiation would be completely dead within a mere 4 hours. It is safe to say this is not exactly the greatest spot to establish a home away from home. Now, when it comes to exploring the wider collection of Jovian satellites, I am only going to touch on them incredibly briefly right now, because I have already put together an entirely separate deep dive video dedicated solely to their details, which you can check out right here. As it stands, Jupiter boasts 67 recognised natural satellites orbiting its bulk. A total of 51 of these objects measure under 10 kilometres in absolute diameter, but the 4 premier satellites, collectively known as the Galilean moons, rank among the absolute largest moons found anywhere in the entire solar system. These major worlds are named Io, Europa, Ganymede, and Callisto, and every single one of them is deeply fascinating in its own highly unique way. Ganymede actually holds the crown as the absolute biggest moon residing in the solar system, boasting a physical diameter that easily outstretches the planet Mercury. With that dramatic final thought in mind, take a close look at Jupiter captured through an infrared lens, which perfectly demonstrates the sheer scale and raw energy output of this world. This distinct dark blemish visible near the bottom of the planet marks the actual crash site of an incoming object from outer space. If that exact same cosmic impactor had somehow struck the Earth instead, it could have easily triggered a global catastrophe that spelled the total end of human civilization as we know it. We can be profoundly grateful that Jupiter is out there doing its job, not just for the breathtaking aesthetic beauty it brings to the night sky, but because in so many hidden ways it serves as an absolute protector and asset to our entire solar system. Thank you so much for tuning in and watching the video this far. Did you pick up some completely new piece of information today regarding Jupiter that you had never encountered before? And what specific planetary remaster project would you love to see tackled next on this channel for this ongoing series? Be sure to share your thoughts with me down below in the comments section, and I will catch you all next time. I think the vast majority of us are well aware of exactly what the individual planets look like when viewed through the standard visible light spectrum. We are all familiar with Saturn's muted golden-yellow presentation, Jupiter's iconic reddish bands and swirling cloud systems, and Neptune's characteristic deep dark blue shade. Be that as it may, light is continuously being pumped out or bounced back by these worlds in a wide array of wavelengths that extend far beyond the organic capabilities of our human eyes, spanning into territories like the infrared and ultraviolet bands. More often than not, the specific data we can harvest by analysing these invisible wavelengths turns out to be vastly more informative and valuable to planetary scientists than simply mapping out how a planet would appear to a normal human eye. That added value exists because specific physical structures or atmospheric features that are completely invisible to our biological sight might show up with absolute clarity when viewed in infrared or ultraviolet light, and the exact same rule applies in reverse. If our goal is to identify exactly what kinds of chemical materials and elements are present on a remote planet, the wider electromagnetic spectrum can step in to guide us yet again. I am Alex Milan, and you are watching Astrum. In this specific segment, I want to focus our attention on exactly what we have managed to uncover by peering through alternative sections of the electromagnetic spectrum at Jupiter and its collection of satellites, and how this unique scientific strategy might hand you a totally fresh perspective on the absolute largest planet in our solar neighbourhood. Just to establish a solid baseline for comparison, let us first take a close look at how Jupiter presents itself when viewed in normal, natural light. The assorted robotic spacecraft that have zoomed past Jupiter over the decades have uncovered an absolutely gorgeous world. The very first thing that will instantly grab your attention when looking at visible light images is the primary main cloud deck of the planet. These are not moisture-filled water clouds like the ones we see floating in the skies of Earth, but are instead made up of frozen ammonia ice crystals. If you study the imagery with a close eye, you can begin to visually map out the varying altitudes of these distinct cloud layers. The dark, thin corridors are actually physical shadows being cast downward by the exceptionally tall, lighter-coloured cloud systems floating above them. It appears that the higher up in altitude these atmospheric clouds climb, the lighter their coloration becomes. A trend that can be seen perfectly in the highest altitude pop-up clouds forming in this specific zone, which show up as a pure, snowy white. The precise mechanical process driving the generation of these diverse colours across Jupiter's wider atmosphere is still not entirely sorted out by science, but it is widely believed to be triggered by the upward churning of chemical mixtures that originally formed deep down within the planet. The moment these materials get lifted up to the highest points of Jupiter's atmosphere, they suddenly find themselves exposed to raw ultraviolet radiation streaming from the sun. This solar exposure causes these compounds to darken, and they eventually begin to sink right back down into the lower atmospheric levels. But as you can clearly observe for yourself, Jupiter's main ammonia cloud deck is entirely opaque. Our eyes are completely unable to see through it. If visible light tracking was the only tool planetary astronomers had at their disposal, the overwhelming majority of Jupiter's interior workings would remain a total locked mystery to us. Fortunately, we also possess specialized scientific instruments that are fully capable of detecting light wavelengths that sit far past our human visual limits, and by tune tracking of specific bands of the infrared spectrum. We can view Jupiter in an entirely unprecedented way. Perhaps the absolute most visually arresting method is to observe Jupiter through the lens of the 4.68 micron wavelength, as this specific band isolates and highlights the internal thermal heat of the planet in a truly remarkable fashion. In this particular thermal view, which was captured by the Gemini Observatory, it is actually the lower altitude, reddish bands that shine out with the absolute highest brightness. You see, Jupiter actually radiates a significantly larger amount of internal thermal energy back out into space than it ever receives from the Sun. The entire planet is actively contracting in total size over time, a gravitational compression that continuously heats up its interior. This internal thermal energy eventually forces its way outward through the dense cloud decks. The escaping heat naturally slips out with the greatest ease wherever the overlying cloud deck happens to be at its absolute thinnest, which perfectly explains why iconic features like the Great Red Spot and the thick white bands seen in visible light turn up as dark, cold zones in this thermal image. Fortunately, we are not just restricted to looking at flat, disc-like views of Jupiter from afar either, thanks to the highly successful Juno spacecraft that is actively maintaining its science orbit around Jupiter right now. By having Juno view Jupiter's polar regions specifically through an infrared lens, planetary scientists were able to stitch together a highly detailed 3D model of the mind-boggling atmospheric vortices that are churning away up there. Jupiter's North Pole features a cluster of 9 seemingly permanent locked vortices, with 8 individual storms arranged in a near-perfect square geometry, all steadily revolving around a single massive vortex situated right at the absolute centre of the pole. Once again, you will instantly spot that it is the lowest altitude atmospheric zones that are radiating the absolute highest amounts of thermal energy. Because this specific wavelength isolates thermal heat and nothing else, the high-altitude atmospheric hazes and physical shadows do not block or distort our view nearly as much as they do when tracking in the visible light spectrum, meaning this technique can hand us an unprecedented window into the genuine three-dimensional layout of these polar storms. Even so, it is worth noting that these regions are still incredibly freezing by normal Earth standards. Even the brightly coloured yellow zones in this data map register at a chilling 13 degrees Celsius, while the darker, high-altitude cloud structures drop all the way down to a freezing 83 degrees Celsius. And because this thermal energy is being generated by Jupiter itself from the inside out. This distinct view remains fully accessible to Juno whether it is tracking the day side or the night side of the planet. The imaging is not reliant on reflected sunlight to work. Furthermore, developing atmospheric storms can frequently show up clearly in infrared data maps, long before they ever become noticeable to astronomers tracking invisible light. Just look at this direct visual comparison captured by the Hubble Space Telescope. These massive, near-Earth-sized tempest systems, which are buried completely underneath the visible upper cloud tops, show up as significantly warmer than the surrounding atmospheric environment, providing a clear indication that Jupiter's internal heat engine plays an absolutely massive role in generating these violent atmospheric disruptions. If we take a moment to look at how specific chemicals are distributed across the surface of Europa, we find that the high concentrations of sulfuric acid tend to group heavily around the planet's visible fractures and cracks. This specific layout strongly suggests that the chemical compound might actually be seeping upward from the massive liquid ocean hidden away directly beneath the frozen outer crust. However, that is not the only place where this material accumulates, as it is also found in high quantities across the trailing hemisphere of the Moon, which is the side shown in the upper left section of this image. The underlying physical explanation for this distribution is that as Europa continuously travels along its regular orbital path around Jupiter, its surface is subjected to a relentless, heavy bombardment of incoming sulfur ions. What makes this interaction truly mind-blowing to contemplate is that this streaming sulfur did not actually originate on Europa at all. Instead, it was originally spewed out into open space by the massive volcanic eruptions actively bursting across its neighbouring moon, Io. Moving our gaze over to a specific impact crater located on the ancient surface of Callisto, we can examine an incredibly detailed data map where high-resolution infrared observations have been carefully overlaid directly on top of a standard visible light photograph. In this unique visual presentation, the regions highlighted in red indicate a heavy presence of pure water ice, whereas the areas shaded in blue point to a much lower concentration of ice. This specific graphic is highly prized by planetary astronomers because it represents one of the single highest resolution infrared data sets we have ever managed to successfully capture of any celestial body orbiting inside the wider Jovian system, with the entire field of view spanning a mere 200 kilometers across. This detailed perspective reveals an immense amount of critical structural information that would remain completely hidden from us if we only had access to standard visible light images. Specifically, it highlights a heavy, dense concentration of water ice sitting directly inside the bowl of the crater itself, but it also reveals a highly distinct circular ring tracing immediately around the outside of the crater rim, where absolutely no water ice is present whatsoever. Then, moving even further outward, water ice suddenly becomes highly visible yet again, spreading along the prominent radiating ray systems that flare away from the primary impact site. The standard explanation for these icier outer zones is that the sheer kinetic force of the original cosmic impactor violently shattered the upper terrain, digging deep enough to expose the hidden layers of pure ice buried directly beneath the surface crust. On the flip side, the existence of that completely dry, ice-free ring sitting right between the central crater bowl and the far-flung debris of the outer ray system continues to be a major scientific mystery for researchers. One leading hypothesis suggests that the icy debris kicked up into space by the initial explosion simply did not begin falling back down to strike the ground until it had travelled that specific distance away from the centre of the blast. Whatever the true mechanical explanation turns out to be, this detailed image provides clear, undeniable proof that non-ice materials make up nothing more than a paper-thin veneer resting on the absolute highest surface layer of Callisto. Now, let us flip our focus back to the giant planet itself and ask what Jupiter actually looks like when we peer through several distinct bands of the infrared spectrum. This particular multi-panel image is exceptionally fascinating to break down. The two images situated at the top left and top right of the display were captured utilizing the 1.61 micron and 2.73 micron wavelengths respectively. and when viewing the planet through these specific bands, the visible cloud decks look remarkably similar to what we are already accustomed to seeing in normal visible light. However, the image placed right in the absolute center of the layout offers a completely different perspective because it was captured tracking exclusively through the 2.17 micron wavelength, which happens to be the primary absorption band of hydrogen gas. As we have already firmly established, Jupiter is overwhelmingly composed of hydrogen material, which means that the moment we look through this specific wavelength, the hydrogen hanging in the atmosphere suddenly becomes completely opaque and highly visible to our instruments. In fact, the only atmospheric features that manage to remain visible in this specific center view are the exceptionally high altitude cloud structures, which are the unique formations that poke up high enough to clear the vast majority of the absorbing hydrogen gas blanket settling below. Shifting down to the bottom row, the image on the left was taken using the 3.01 micron band, where a modest amount of light absorption is occurring, though it is nowhere near as intense as the absorption seen in the hydrogen band. At this specific frequency, it is methane gas and ammonia vapor that are actively absorbing the incoming light waves. The image resting in the bottom middle was captured at 4.99 microns, handing us yet another highly detailed thermal heat map of the planet's interior energy leaks. Finally, the image placed in the bottom right corner represents a highly complex false color combination that systematically fuses all 5 of these individual wavelength views into a single composite frame. This composite explains exactly what is happening behind the scenes whenever you encounter a false color space image featured in an astronomical documentary, as it demonstrates how scientists use these arbitrarily assigned color schemes to make highly complex data visually digestible. The final highly compelling view of Jupiter that deserves our close attention is captured within the ultraviolet spectrum. Generally speaking, utilizing absorption spectroscopy inside the ultraviolet band is not considered a particularly useful or common strategy within the field of planetary astronomy. In fact, the only prominent historical instance where this specific technique was actively and intensively utilized on Jupiter occurred back in 1994, when astronomers used it to meticulously track the historic impact of comet Shoemaker-Levy 9. During that monumental cosmic collision, the massive clouds of dust kicked up by the fragments absorbed an enormous amount of the incoming ultraviolet sunlight, which allowed researchers to easily track the high-altitude wind patterns circulating through the planet's stratosphere by closely monitoring how those dark features evolved over time. Be that as it may, chemical molecules that are energized to sufficiently high temperatures will naturally emit their own light across a wide variety of differing wavelengths, and there happens to be an incredibly bright, continuous source of light screaming away from Jupiter in both the ultraviolet and infrared bands, its auroras. Jupiter's polar auroras are unbelievably powerful when compared to the modest northern and southern lights we experience on Earth, and they represent a permanent, never-ending feature of the planet. The Hubble Space Telescope, which possesses the specialized ability to see in ultraviolet light, has been continuously monitoring and tracking Jupiter's auroras for decades. Even so, the absolute best and most detailed close-up views of these polar light displays have actually been delivered by the Juno spacecraft operating in the infrared band, a superiority that comes down entirely to Juno's unique orbital path, which sends it directly over the planet's poles. In contrast, Hubble's distant viewing angle from Earth makes detailed polar observations exceptionally difficult to execute. These magnificent auroras are driven by the intense magnetic field environment of Jupiter, which continuously funnels high-energy particles down into the upper atmosphere, while also receiving a steady supply of matter from the massive electrical flux tubes physically connecting the giant planet to its orbiting moons. So, there we have it, a comprehensive look at Jupiter through a totally different set of eyes than the ones you are likely used to using. As we have clearly demonstrated, tracking chemical absorptions and glowing fluorescence through the power of spectroscopy can help us comprehend the inner workings of a remote planet far more deeply than visible light observations ever could on their own. By employing these techniques, we can accurately identify specific molecules and minerals map out a planet's internal heat signatures, and observe powerful auroras interacting directly with the surrounding magnetosphere. Fusing all of these diverse data sets together is what ultimately allows humanity to construct a truly complete picture of how a giant world operates and why it behaves the way it does. Let us now travel back in time to July of 1994, when scientists and stargazers all across the globe watched in absolute amazement as Comet Shoemaker Levy 9 slammed directly into Jupiter. The raw kinetic energy unleashed by this cosmic blast was so incredibly immense that it produced an explosion equivalent to 300 million atomic bombs detonating all at once. For 6 consecutive days, the face of Jupiter was brutally throttled by 21 separate sequential impacts as the shattered fragments of the comet plunged into the atmosphere one after another. These violent collisions generated colossal plumes of superheated debris that climbed to an astonishing 3,000 kilometers above the upper cloud, tops a truly mind-boggling physical feat when you consider just how powerful Jupiter's downward gravitational pull is. Furthermore, these impacts instantly superheated the surrounding atmosphere to temperatures scaling all the way up to 30.00 degrees Celsius at the exact coordinates of the strikes. At the precise moment it entered the atmosphere, the comet was moving at a blistering velocity of 216,000 kilometers per hour, with its single largest individual fragment measuring a massive 2 kilometers in absolute diameter. The resulting impact plumes kicked up giant clouds of dark debris that remained clearly visible to telescopes for months, leaving a collection of dark scars slashed across Jupiter's atmosphere that was significantly more prominent and easier to see than the Great Red Spot itself. Now, planetary collisions of this monumental scale are not entirely unheard of in the grand history of our solar system, which is heavily littered with physical evidence of major asteroid and comet impacts. For instance, scientists are widely convinced that the Earth was struck by a truly colossal asteroid at the very end of the Cretaceous period, an event that triggered a global climate catastrophe and led to the total extinction of the non-avian dinosaurs. However, events of this destructive magnitude are extraordinarily rare in the modern era, meaning that getting the chance to witness one happening live in real time represents a true once-in-a-lifetime opportunity for humanity. So, what did this historic event actually look like from our perspective, and does this violent incident shed any critical light on the actual mathematical odds of a similar extinction-level catastrophe happening here on Earth? In the year 1993, astronomers Carolyn and Eugene Shoemaker, alongside their colleague David Levy, were conducting routine observational research at California's famous Palomar Observatory when they suddenly discovered a highly unusual periodic comet that had been firmly captured by Jupiter's immense gravitational net. Describing a comet as periodic simply means that it maintains an orbital loop around its primary body that takes fewer than 200 years to complete. This specific discovery was highly unusual because the vast majority of comets residing within our solar system maintain paths that circle directly around the Sun. However, Jupiter is so incredibly massive, holding the title of the largest of the 8 planets by a wide margin, that its inherent physical ability to snare passing objects that drift too close to its orbital territory is not surprising at all. In fact, a large percentage of Jupiter's outer irregular moons are highly suspected to be captured asteroids and comets that have simply burned off all the volatile, icy materials that used to coat their surfaces long ago. But this specific comet boasted a handful of other highly unique characteristics that instantly set it apart. For one thing, it was exceptionally large, so large, in fact, that planetary scientists calculate that an impact of this scale is a rare 1 in 6,000 year occurrence. Furthermore, the comet was already heavily fragmented, having most likely been violently ripped apart by Jupiter's crushing gravitational tidal forces during a previous close approach. Most striking of all, however, was the comet's highly eccentric orbital path. In the field of astronomy, eccentricity is the formal mathematical measurement of how much a celestial orbit deviates from a perfect circle, where a value of 0 indicates a flawless circle and a value of 1 marks the absolute upper limit where an elliptical path stretches into a hyperbolic trajectory. Shoemaker-Levy-9's calculated path boasted an extreme eccentricity value of over 0.998, making it incredibly elongated. Almost immediately after charting this path, astronomers realized there was a distinct mathematical possibility that the comet was steering on a direct collision course with Jupiter, and that suspicion solidified into absolute certainty once they managed to collect more precise tracking data. Before long, astronomers knew with complete confidence that the final impact would occur sometime during July of 1994, and the entire world began waiting for the historic event with bated breath. Anticipating the arrival of the impact, astronomers around the globe pointed their premier instruments toward the giant planet, including the powerful Keck Observatory, Germany's Rosat X-ray telescope, and NASA's Hubble Space Telescope. But the moment the very first fragment struck on July 16, 1994, a worst-case scenario occurred that threatened to completely ruin the show. The problem lay in the comet's final trajectory, which dictated that the actual impact sites would all be located on the far side of Jupiter, completely facing away from Earth. This layout meant that not a single high-powered telescope stationed on the surface of our planet was in a physical position to directly view the initial explosions. For the global scientific community, this obstacle would have been an absolutely crushing disappointment, but by a stroke of sheer luck, not all of humanity's cameras were marooned on Earth. By pure unbelievable coincidence, NASA's Galileo spacecraft, which had been launched back in 1989, was sitting exactly 1 year away from reaching its final orbital destination at Jupiter during the time of the comet's final approach. It just so happened to be cruising through a flawless vantage point to record the explosions exactly as they erupted. And Galileo was not our only robotic assistant watching from afar either. The Ulysses spacecraft, which had been launched in 1990 to study the Sun, was also successfully maneuvered to look at Jupiter. And even NASA's venerable Voyager 2 probe, located at a remote distance of 44 astronomical units away, was carefully programmed to track radio emissions originating from the crash site using its onboard ultraviolet spectrometer. Every single one of these deep space probes temporarily paused its own primary science mission to cooperate, working in tandem to help humanity witness an extraordinary cosmic event. Shortly after the initial chunk, designated Fragment A, slammed into the planet, Galileo observed a truly massive fireball erupt from the cloud tops, with temperatures instantly peaking at an incredible 24,000 degrees Celsius. The resulting plume of superheated material expanded upwards so rapidly that it quickly reached an altitude of 3,000 kilometers, a dimension that would make it as wide as the continent of Australia from north to south. This was highly surprising to researchers, as the global scientific community had not expected to see such dramatic fireballs form in the immediate aftermath of the collisions. A few minutes later, massive clouds of ejected debris began plunging right back down toward Jupiter's surface, burning up a second time as they fell and turning the upper atmosphere into a raging furnace. Before long, Jupiter's rapid rotation brought the fresh impact site directly into the field of view of Earth, allowing high-power telescopes like Hubble to capture clear images of a giant dark blemish on the planet's face. As we noted before, Jupiter spins at a very high velocity, with a full day lasting a mere 10 hours. Contrary to what your intuition might tell you, the larger planets in our solar system tend to possess significantly shorter day lengths than the smaller, rocky world. The energetic impact of the comet fragments also triggered powerful shockwaves that rippled across Jupiter's dense atmosphere at a velocity of 450 meters per second, and all of this incredible destruction was generated by just the first single fragment. For 6 consecutive days, between July 16 and July 22, the remaining train of comet fragments continuously bombarded Jupiter. The single largest explosion occurred on July 18, when fragment G struck the planet. This single impact produced a blast, that was an incredible 600 times more powerful than the combined nuclear arsenal of the entire human race, leaving behind a massive dark scar that stretched wide enough to match the entire diameter of the Earth. However, as spectacular and visually arresting as the initial impacts were, the long-term aftermath of the comet proved to be just as scientifically valuable. By carefully studying the evolving clouds of dark debris, scientists were handed an unprecedented, clear window into the high-altitude circulation patterns of Jupiter's atmosphere. In addition, they caught a never-before-seen glimpse into the chemical composition of Jupiter beneath its impenetrable upper cloud layers. Because spectroscopic instruments were able to identify the exact materials that had been violently splashed upward from the deep interior by the force of the explosions. They successfully detected diatomic sulfur and carbon disulfide alongside heavy elements such as silicon, iron, and magnesium. Interestingly, they also registered substantial quantities of water vapor, a chemical presence they were not necessarily expecting to find out there. In fact, one of the primary science objectives assigned to NASA's modern Juno probe is to locate exactly where this water is hiding inside Jupiter's atmosphere. However, one of the more disturbing and sobering implications of this event was the sudden, undeniable realization that large, destructive celestial bodies can still collide with major planets in the modern era. For a long time, one school of thought argued that massive comet and asteroid collisions were a feature confined to the chaotic, early days of the solar system's formation. But Shoemaker-Levy 9 made it crystal clear to everyone that highly destructive collisions are still entirely possible today. Had we simply lucked out and witnessed an extremely rare cosmic anomaly, or do these types of impacts happen far more frequently than anyone had previously estimated? We must remember that humanity has only possessed the advanced technology required to observe this kind of deep space event within the last 80 years or so. If a comet as large as Shoemaker-Levy 9 were to strike the Earth today, it would trigger a global extinction event that wiped out the vast majority of life on our planet. This realization had a dramatic and lasting effect on our collective cultural psyche. As anyone who lived through the 1990s can easily recall, it also served as a massive, urgent wake-up call for NASA and various international defense organizations. Before the impact of Shoemaker-Levy 9, the term planetary defense did not even exist within the global lexicon, but in the immediate wake of the disaster, NASA formally took up the vital mission of locating and tracking near-Earth objects, or NEOs. Their initial goal was to identify at least 90% of all asteroids in our orbital neighborhood that measured greater than 1 kilometer in diameter, and having successfully achieved that milestone, NASA is now well on its way toward cataloguing asteroids down to a size of 140 meters. But before you stay up all night worrying about a sudden cosmic impact, you should know that these events are undoubtedly rare. And there is one other major silver lining to take away from the Shoemaker-Levy 9 impact. You see, Jupiter is a truly massive world with a dominant gravitational pull, and because it sits out on the perimeter of the inner solar system, some planetary scientists now believe it acts as a giant cosmic vacuum cleaner for our neighborhood. We know from statistical models that Jupiter experiences roughly 2,000 to 8.00 times as many comet impacts as the Earth does, so it is highly probable that the primary reason extinction-level impacts are so incredibly uncommon on Earth is that Jupiter has been continuously operating as a giant gravitational magnet, sweeping up these dangerous comets and asteroids before they can ever drift into the inner solar system. This compelling argument has even been formally integrated into the famous rare earth hypothesis, which suggests that our home planet benefits from a highly specific, unique set of cosmic conditions without which the evolution of complex, intelligent life would be completely impossible. Not everyone in the scientific community agrees with this hypothesis, of course, and we are still a very long way from proving it beyond a shadow of a doubt. So, while we might not know the exact mathematical likelihood of a massive comet or asteroid striking the Earth tomorrow, The historic impact of Shoemaker-Levy 9 with Jupiter has vastly advanced our scientific understanding of these chaotic events. Moreover, it was without question a spectacular and historic moment that treated onlookers to one of the most impressive action scenes ever witnessed by human eyes. Perhaps one day in the future, we will have the opportunity to witness something even bigger, but hopefully, we will be watching it from a very safe distance away. While our planet has experienced its own explosive events in recent times, such as the colossal 2022 Tonga volcanic eruption, for now, the absolute winner of the title remains completely clear. The single largest explosion ever witnessed on a planet by human eyes belongs to Shoemaker-Levy 9, and by comparison, any competition on Earth looks like nothing more than a tiny drop in a bucket. While the major planets naturally tend to hog all the attention in school classrooms and space agency press releases, there are smaller, lesser-known worlds operating inside our solar system that are every bit as compelling and interesting to study. 4 of these exceptional worlds are collectively known as the Galilean moons, which comprise Jupiter's 4 largest natural satellites. When you consider just how close to one another these worlds reside, it is truly fascinating to see how radically different they are from one another. In this single collection, you have an ultra-volcanic moon, a frozen moon that represents one of the absolute best candidates for harbouring alien life anywhere else in the known universe, the single biggest moon in the entire solar system, and an ancient, heavily scarred world whose surface features can be traced all the way back to the very dawn of the solar system's creation. In this segment, we are going to explore these exceptional worlds one by one, conducting a comprehensive deep dive into the unique physical attributes that make each one so special. By the time we reach the end of this I am completely confident you will understand exactly why these worlds are becoming the primary targets for 2 separate, highly advanced space missions launching this decade from both NASA and the European Space Agency. We will begin our journey with the innermost satellite of the group, the fascinating moon Io. To truly appreciate this world, let us first get to know the structural context of Io's neighbourhood a little bit better. Jupiter possesses 79 confirmed moons that we have managed to discover up to this point in time. There are a few tiny minor moons that orbit exceptionally close to the planet, threading their paths in and around the thin planetary ring system. Moving past those inner structures, you encounter the 4 massive satellites known as the Galilean moons, named in honour of Galileo Galilei, who first discovered them through his primitive telescope back in the year 1610. Arranged in order from the innermost path to the outermost orbit, these major moons are Io, Europa, Ganymede, and travelling past their domain brings you into the realm of Jupiter's outer irregular moons, all of which occupy paths that sit vastly further out into open space than the 4 main worlds. Io maintains an orbit that sits incredibly close to Jupiter, flying a mere 350,000 kilometres above the upper Jovian cloud tops. To put that into perspective, if you were to stand on the surface of Io and look up into the sky, the giant disk of Jupiter would appear a staggering 39 times larger than our moon looks to us from Earth. Furthermore, Io zips around Jupiter at an incredible pace, completing a full orbit in just 42.5 hours, which stands in sharp contrast to the month-long orbital journey required by our own moon. At certain specific points along this tight orbital path, the intense gravitational pull creates a physical tidal bulge on Io that is estimated to stretch up to 100 meters high. This dramatic stretching effect is fundamentally identical to what we see happening on Earth, where our ocean tides are continuously driven by the gravitational pull of the moon, though the physical scale of the effect on Earth is vastly more minimal, with the oceans usually shifting a mere 2 meters from high tide down to low tide. In comparison, Io is subjected to an incredible 300% more tidal force than our moon exerts on. This extreme stress exists because of its close proximity to the absolute largest planet in our solar system, and because the other massive moons locked in the system refuse to allow Io's orbital path to become any less eccentric over time. meaning that Io is absolutely not going to be receiving any kind of physical respite anytime soon. A single local day on Io lasts the exact same amount of time as its orbital revolution, which means that Io is tidally locked to Jupiter. Just like the mechanical arrangement where we can only ever see one single face of our moon from the surface of the Earth, only one specific side of Io ever faces toward Jupiter as it makes its rounds. Io is a relatively large satellite, and although it ranks as the second smallest world among the 4 Galilean moons, it is quite comparable in absolute size to Earth's moon and shares a nearly identical density, meaning it generates a similar level of surface gravity. But interestingly enough, it does officially claim the title for having the highest density of any known moon operating anywhere in the entire solar system, which represents just one of its many unique physical signatures. Another defining characteristic is that it is composed almost entirely of solid silicate rock and metallic iron, which makes its internal structural layout highly similar to the terrestrial rocky planets and our own moon. This stands in stark contrast to the vast majority of other large moons found throughout the outer solar system, which are typically constructed out of a mixture of water ice and silicates. In fact, Io possesses the absolute least amount of water of any known solid body residing in the entire solar system. Its central core is highly believed to be constructed out of pure iron or iron sulfides, which is wrapped in a thick, silicate-rich mantle and outer crust. However, this dense core is not believed to be undergoing active thermal convection, because scientific instruments have never detected any kind of independent magnetosphere surrounding the moon. The underlying mantle layer is thought to be largely liquid near the upper crust, measuring at least 50 kilometers in total thickness, and this hidden magma layer is the exact location where all of the world's frantic surface volcanism originates. This brings us directly to what is easily the single most interesting and mind-boggling attribute regarding Io, the presence of hundreds of massive active volcanoes tearing open its surface. Before the decade of the 1970s arrived, humanity understood next to nothing about the true nature of Io, though Earth-based telescopes were beginning to pick up subtle spectroscopic hints that the moon was completely devoid of water ice and likely featured a surface dominated by raw sulfur. The very first robotic space mission to capture Io in any real degree of detail was Pioneer 11. And although the actual image quality was still quite poor by modern standards, the probe did successfully detect that Io was made out of solid silicate rock rather than water ice, and that it harboured a paper-thin atmosphere. Pioneer 10 was also originally scheduled to capture a series of historic close-up photographs of Io during its flyby, but that entire dataset was completely lost, because Jupiter's intense radiation fields severely interfered with the spacecraft's onboard command systems. To understand what went wrong, you have to realize that the radiation belt Pioneer 10 drove through was a staggering 10,000 times stronger than the maximum radiation levels measured around the Earth. The next major voyages sent to Jupiter were the historic Voyager 1 and Voyager 2 missions in 1979. Voyager 1 made its close approach at a distance of only 20,000 kilometers, allowing its cameras to capture a series of deeply impressive close-up images of Io's surface. What the mission team saw on their screens was a truly remarkable landscape filled to the brim with vibrant alien colours and a total unbelievable absence of impact craters. Instead of craters, the probe discovered towering mountains that climbed significantly higher than Mount Everest, alongside massive volcanic pits stretching hundreds of kilometers wide, and what appeared to be active flows of liquid lava. Most notably of all, however, was the undeniable presence of active volcanic plumes screaming away from the surface. This monumental discovery provided absolute proof to the world that Io is volcanically active, and it still holds the title of the first and only place in the universe where active volcanism has been visually witnessed outside of the Earth, not counting cold cryovolcanoes. Voyager 1 also successfully confirmed that the outer surface of Io is completely blanketed in diverse formulations of sulfur frosts, and this chemical coating is what gives Io its highly characteristic multicolored palette, it found that these sulfur compounds completely dominate the local atmosphere. Voyager 2 also observed Io in July of 1979, but it conducted its observations from a much greater distance of 1 million kilometers away. Despite being that far off, its cameras still successfully captured 7 out of the 9 active volcanic plumes that Voyager 1 had originally discovered 4 months earlier, proving that these massive volcanoes had remained continuously active throughout that entire time frame. However, the truly revolutionary close-up images of this world were delivered by the Galileo spacecraft, which successfully arrived in orbit around Jupiter in 1995. The spacecraft was not explicitly designed to focus solely on studying Io, but it was still able to acquire some of the single highest resolution images we possess of its surface today. Sadly, Galileo was never able to operate at its full scientific capacity because it suffered several severe mechanical malfunctions during its journey, which means we could have received even more spectacular data had the probe been fully operational. What it was able to see, however, were active plumes bursting from a multitude of volcanoes, while also confirming that these features are actively erupting pure sulfur and silicate magmas, quite similar to the volcanic activity we see on Earth, with the unique exception that the magma on Io is also exceptionally rich in magnesium. The resulting surface of Io is spectacularly colourful to behold. The brilliant yellow patches you see are composed primarily of raw sulfur, while the bright white zones are mostly made out of freshly deposited sulfur dioxide frosts. Moving up toward the polar territories, the surface sulfur is heavily damaged by incoming radiation, which can be clearly seen as the poles take on a much redder appearance than the rest of the world. In various other locations, the deep shades of red represent the chemical deposits left behind by massive volcanic plumes that soared hundreds of kilometers out into space above Io. The single most obvious and prominent volcanic deposit visible on the Moon is generated by the legendary volcano named Pele. The single most obvious and prominent volcanic deposit visible on the Moon is generated by the legendary volcano named Pele. It is quite unfortunate that this colossal geological feature happened to be completely inactive during the specific years when the Galileo spacecraft was actively touring the system, but we are incredibly lucky that Voyager 1 was operational and in the perfect position to witness a massive active plume erupting from the site when it made its historic close pass in 1979. In the stunning image captured by Voyager's cameras, this immense umbrella-shaped cloud of volcanic material is seen climbing to a mind-boggling altitude of 300 kilometers above the terrain, while fanning out to an absolute width of 1,200 kilometers across the surface. To help your mind comprehend the sheer physical magnitude of that feature, a volcanic plume of those exact dimensions would be roughly the same size as the entire state of Alaska. Interestingly, when we examine the structural anatomy of lava flows here on Earth, the primary source of the liquid magma is almost always a prominent, cone-shaped depression situated right at the absolute peak of a towering mountain. However, when you look at the landscape of Io, these traditional volcanic peaks with mountaintop depressions are completely missing from the terrain. Instead of high volcanic mountains, Io features massive flat volcanic depressions that are structurally classification defined as lava lakes, which are bounded by incredibly steep, towering vertical walls along their outer perimeters. The absolute largest and most dominant of these volcanic depressions found anywhere on the surface of Io is a legendary formation named Loki, which spans a massive 200 kilometers in total diameter. These unique features are directly connected to the immense, pressurized reservoirs of liquid magma churning deep below the crust, but under normal conditions, the top of the lake is covered by a thin, dark layer of solidified rock crust. On a regular day, this single volcanic feature produces an astonishing 25% of the total thermal heat output radiated by the entire moon of Io. However, at semi-regular intervals, a dramatic physical process occurs where the heavy cooled crust resting on the surface of the lake fractures and begins sinking back down into the molten depths below, which exposes the raw lava underneath and causes Loki to suddenly produce 10 times more thermal heat energy than it normally does. This fascinating and chaotic recycling process can be observed with exceptional clarity at one of Io's other major volcanic centers, a feature named Tivashtar. Under normal quiet conditions, this specific volcanic region looks relatively calm, but during a major eruption event, the solid surface crust can be seen peeling away and plunging directly into the boiling lava lake. In one famous close-up photograph captured by our probes, there are regions of the image that show up as nothing but pure, overexposed white, because the raw radiant energy beaming from the massive curtain of fountains was so intensely bright that the camera's digital sensors could only register it as solid white. In the year 2007, NASA's New Horizons spacecraft utilized the massive gravitational field of Jupiter to execute a vital gravity assist maneuver, picking up the necessary velocity it required to complete its long journey out to Pluto. The mission team wisely used this close encounter as a perfect opportunity to rigorously test the probe's advanced scientific equipment and long-range lenses. They focused their cameras directly on Io during the brief flyby, and the data they received back on Earth was nothing short of absolutely amazing. The Tivashtar volcano, which we just discussed, happened to be in the middle of a full-scale, violent eruption at that exact moment, and its massive plume was captured soaring hundreds of kilometers into space above Io's surface. The high-resolution cameras were also able to detect a multitude of smaller volcanic eruptions popping off all across the surface of the Moon. I must freely admit that this specific sequence of images represents one of the single most visually impressive and breathtaking things I have ever seen in the entire history of space exploration. Even though the vast majority of Io's active volcanoes tend to be completely flat structures that sit flush with the surrounding plains, the Moon does happen to harbour some extraordinarily tall rocky mountains, with the single highest peak climbing to an astonishing altitude of 18 kilometres. What makes these giant mountains particularly unique is that they tend to stand completely by themselves as isolated blocks, rather than forming part of a continuous ridge or mountain range. Furthermore, although the vast majority of these high peaks are not volcanic in nature, massive lava lakes are frequently found sitting directly near their bases, which strongly indicates to structural geologists that deep faults and fractures exist in the crust immediately adjacent to these mountains. Another truly unique and fascinating aspect of Io is the complex way it physically interacts with the immense magnetic field of Jupiter. As we have already established, Jupiter possesses an exceptionally large and powerful magnetosphere, and Io's tight orbital path forces it to plough directly through some of the absolute strongest sections of this magnetic field environment. The unusual and mind-blowing thing about this interaction is that as high-energy particles escape from Io's thin atmosphere and volcanic plumes, they are quickly lost to open space and become trapped in orbit around Jupiter, forming a massive structure known as a neutral cloud. This giant cloud of neutral particles extends far ahead and behind Io along its orbital path, while also wrapping completely around the giant planet itself. But that is not all, because sitting directly within this zone is another massive structure known as the plasma torus, which is a giant donut-shaped ring of ionized particles that is locked to the rapid rotation of Jupiter's internal magnetic field. This plasma torus rotates at a much faster velocity than Io travels, screaming along at a blistering 70 kilometers per second, whereas Io moves along its orbital path at a more modest 17 kilometers per second. This speed differential means that Io is constantly ploughing right through the middle of the torus, causing the high-energy ionized particles within the donut to continuously bombard the neutral cloud, exciting those particles to much higher energy levels. These newly ionized particles are then instantly pulled into the torus by the powerful magnetic field lines, creating a self-sustaining loop. This continuous stripping process drains matter from Io's neutral cloud into the plasma torus at a staggering rate of roughly 1 ton of pure material every single second, an influx of mass that vastly increases the physical size and strength of Jupiter's overall magnetic field. In fact, If Jupiter's immense magnetosphere were somehow visible to the naked human eye from Earth, it would appear about the same size as the full moon looks in our night sky. The intense physical connection between Io and Jupiter does not stop there. Either the powerful magnetic field lines of Jupiter, which Io is constantly cutting across, physically couple the moon's local atmosphere and neutral cloud directly to Jupiter's upper polar atmosphere. This connection generates a massive, continuous electrical current that flows along what scientists formally refer to as the Io flux tube. A flux tube is essentially a dense, highly concentrated bundle of magnetic field lines. We can see identical structures operating on the Sun between active sunspots, where they become highly visible to our instruments due to the streams of charged plasma flowing along them. Io's flux tube funnels so much electrical energy down into Jupiter that it leaves a permanent, bright aurora trail tracing around the planet's poles. In fact, when looking at satellite images of Jupiter's polar auroras, you can clearly see the exact footprint where the flux tube from Io strikes the upper atmosphere. Spectacular auroras are also highly visible on Io itself, though they are not confined to the polar regions. When observing these alien light displays, the differing colours reveal the exact types of particles being ionized in the atmosphere. Green indicates sodium, red points to oxygen, and blue signals sulfur. Now, let us move outward to the next world in the system, Europa, which stands as one of the single most exciting and tantalizing moons in the entire solar system. It is a beautiful, smooth world filled to the absolute brim with deep scientific mysteries. The very first close-up photograph humanity ever acquired of Europa was captured by the Pioneer probe all the way back in 1973, and since that historic encounter. The moon has been visited by both the Voyager and Galileo spacecraft. With each subsequent robotic visit, Europa has never failed to completely surprise and amaze the scientific community. While it is true that we are still a very long way from solving all of Europa's complex structural puzzles, planetary scientists are finally beginning to successfully piece together how this fascinating world works. To understand its nature, let us first look at where Europa fits into the wider Jovian family layout. Europa holds the title for being the second closest and the absolute smallest of the 4 Galilean moons, though it is still large enough to rank as the 6th largest natural satellite in the entire solar system, sitting just slightly behind Earth's moon with an absolute diameter of roughly 3,000 kilometers. It requires 3.5 Earth days to complete a single full orbit around Jupiter. Interestingly, the 3 innermost Galilean moons, Io, Europa, and Ganymede, are firmly locked together in a strict 4000-1 orbital resonance due to their mutual gravitational influence on one another. This orbital resonance ensures that for every single orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This constant gravitational tug-of-war prevents Europa's orbital path from ever settling into a perfect circle, forcing it to remain slightly elliptical over time. Because Europa maintains this slightly elliptical path, the absolute magnitude of the gravitational pull acting upon it from giant Jupiter continuously increases and decreases as the moon loops closer and further away. This continuous variation creates massive tidal forces that physically stretch and flex the moon's solid surface. These internal mechanical forces are incredibly significant because they exert a massive influence on the moon's overall physical appearance and drive everything that happens beneath its frozen outer shell. Generally speaking, Europa's outer surface is composed almost entirely of pure water ice. When you look at an image of the moon, it features a remarkably distinctive and unmistakable landscape crisscrossed by thousands of long, continuous fractures and dark cracks. These prominent markings are formally called lineae, which is simply the Latin word for lines. These lineae are typically quite narrow, measuring a mere 1 to 2 kilometers in total width. But they routinely extend for thousands of kilometers across the face of the moon. While scientists are still debating the exact mechanical process behind their formation, The leading theory suggests that as the frozen crust pulls apart due to tidal flexing, warmer, slushy material from deep below wells up to fill the gap, operating in a fashion that is remarkably similar to the mid-ocean ridges found on Earth. In high-resolution images captured by the Galileo spacecraft, you can also see a multitude of small, dark brown spots scattered across the plains. These circular features are relatively small, spanning about 10 kilometers across, and they are known as lenticulae. Geologists believe they are formed by the slow upwelling of warm, low-density ice rising toward the surface, either by bowing the crust upward or by shattering it completely. Whenever this underground material successfully shatters through the frozen crust, it creates highly complex, chaotic landscapes that planetary scientists formally refer to as chaos terrains. These features look like incredibly rough, jumbled patches of broken ice blocks surrounded by otherwise smooth plains. Scientists expect these specific spots to be relatively soft and warm, meaning they likely contain an absolute treasure trove of critical information about what is happening directly beneath Europa's crust. Furthermore, analytical data collected by the Galileo probe indicated that Europa's equatorial regions might be completely covered in a dense wilderness of jagged ice spikes called penitentes. These sharp, vertical formations can reach up to 15 meters in height and are believed to form via sublimation driven by direct overhead sunlight at the equator. Interestingly, penitentes can be found right here on Earth in cold, dry, high-altitude desert environments, though they never grow anywhere near as large as the giant versions operating on Europa. Despite the fact that Europa is roughly the exact same age as the rest of our solar system, its surface is almost completely devoid of impact craters. In fact, scientists have only managed to locate fewer than 50 major craters across the entire Moon, which stands in stark contrast to Earth's Moon, which features more than 5,000 craters with diameters greater than 25 kilometers. This absolute lack of cratering provides clear, undeniable proof that Europa's surface is incredibly young, dynamic, and constantly renewing itself over time. This continuous surface renewal strongly implies that the ice shell is resting on top of a global ocean of liquid water, kept warm by the friction of tidal flexing. Calculations suggest that this subsurface ocean contains more than twice the amount of liquid water found in all of Earth's oceans combined. Because liquid water and internal heat energy are the two primary ingredients required for the existence of life, Europa represents the single most promising target in our search for extraterrestrial biology. To find out for certain, space agencies are preparing to send sophisticated probes to investigate this icy world more closely. Let us now shift our attention out to the third Galilean satellite, the colossal world known as Ganymede. As we noted previously, Ganymede officially holds the title of the absolute largest moon in the entire solar system, boasting a physical diameter that is actually larger than the planet Mercury. If Ganymede were orbiting the Sun independently, rather than being snared by Jupiter, it would easily qualify as a full-fledged planet in its own right. Unlike its inner neighbours, Ganymede possesses its own independent, internally generated magnetic field, a unique attribute that sets it apart from every other moon in the solar system. This independent magnetosphere creates its own distinct auroral displays that shimmer near the moon's poles. When scientists used the Hubble Space Telescope to watch these auroras bobbing back and forth, they noticed that the movement was being suppressed by some massive internal force. The only logical physical explanation for this dampening effect is the presence of a vast electrically conductive layer buried deep beneath the surface specifically, a massive underground ocean of salty water. Finally, we reach the outermost of the four major satellites, the ancient world called Callisto. Callisto is a remarkably different world compared to the other three, defined primarily by its complete lack of internal activity and tidal heating. Because it orbits at a much greater distance from Jupiter, sitting roughly 1.9 million kilometers, it does not experience the intense gravitational squeezing that drives the volcanoes of Io or the renewing ice shelves of Europa. As a direct result, Callisto is a geologically dead world whose surface has remained completely unchanged for billions of years, making it the most heavily cratered object found anywhere in the solar system. Its ancient crust is completely saturated, with impact scars piled on top of one another, preserving a flawless physical record of the early solar system's violent history. The physical volume of the moon Ganymede is roughly 26% greater than that of the planet Mercury, even though it does not possess nearly as much total mass. This specific mass difference is reflected in Ganymede's average density, which registers at a modest 1.9 grams per cubic centimetre, especially when you compare it directly to Mercury's much higher density of 5.4 grams per cubic centimetre. The primary reason for this low density lies directly in its internal material composition, in a manner that is highly structurally similar to its neighbouring world Europa. The outer surface of Ganymede is composed of a massive, dense crust of pure water ice that plunges downward to an absolute depth of roughly 150 kilometres. Sitting directly beneath this frozen outer barrier is a feature that planetary scientists believe is a colossal global ocean composed of liquid water. When we call this ocean vast, we are not exaggerating in the slightest. Because while a world like Mercury is exceptionally dry and composed almost entirely of dense metals, the sheer abundance of water hidden inside Ganymede drastically lowers its overall average density. In fact, the subsurface ocean of Ganymede is so incredibly large that it contains more liquid water than all of the surface oceans, seas, and rivers on Earth combined. Analysts estimate that this underground sea has an average depth of 100 kilometres, a figure that makes it 10 times deeper than the absolute deepest trenches found in Earth's oceans. Because of this massive water content, the total structure of Ganymede is only 50% rock, while the remaining half is composed entirely of water and minor amounts of metals and other specialised ices. This composition seems incredibly appropriate when you consider the classical mythology behind its name, where the king of the gods, Zeus, or Jupiter as the Romans called him, chose a young boy named Ganymede to serve as the official cupbearer for the gods. It feels incredibly fitting that the moon Ganymede would happen to carry such a massive supply of water around as it orbits its parent planet Jupiter. Interestingly, advanced scientific data reveals that Ganymede possesses its own dedicated thin atmosphere that contains molecular oxygen. Now, when you hear about a world that possesses both a massive internal ocean and an oxygen-rich atmosphere, you might naturally begin to wonder if it is completely possible that alien life forms exist inside Ganymede. While the emergence of life is certainly a physical possibility, there are several key structural features of Ganymede that make the development of biology rather unlikely. To begin with, the oxygen atmosphere itself is incredibly thin and tenuous. Specialists estimate that the total atmospheric pressure sitting on the surface rests somewhere between 0.2 and 1. 2 micropascals, a value that translates to roughly 100 billion to 500 billion times less than the atmospheric pressure experienced at sea level here on Earth. For a human explorer, that would make the air absolutely impossible to breathe. Furthermore, while our own planet Earth has continuously demonstrated that complex biological ecosystems can easily flourish in the deepest. Darkest sections of our oceans, without ever needing direct sunlight to sustain them, there is a massive internal barrier that likely prevents this same process from happening inside Ganymede. This barrier exists because the subsurface ocean of Ganymede is so incredibly deep that the liquid water resting at the very bottom of the sea would likely be compressed back into a solid ice phase by the sheer, crushing weight of the water above it. Biological life in the absolute deepest zones of Earth's oceans is able to survive and thrive thanks to rich minerals and heat being continuously ejected from active geothermal vents on the seafloor. However, with such a thick, dense layer of compressed ice sitting directly between the rocky core and the liquid ocean, it is highly unlikely that these vital geothermal vents can interact with the water on Ganymede. Because of this specific structural layout, Ganymede's neighbouring moon, Europa, is widely considered by astrobiologists to be a far more promising candidate for the discovery of alien life. However, if Ganymede's global ocean happens to be highly salty, a possibility for which there is an increasing amount of scientific evidence, it could change the entire interior makeup of the Moon drastically. Advanced theoretical models suggest that within a highly saline ocean, the internal water structure could potentially organize into multiple distinct liquid layers that are completely separated from one another by horizontal sheets of ice. If this complex multi-layered scenario is actually what is happening, the absolute lowest and most internal liquid layer could indeed be sitting in direct physical contact with the Moon's hot rocky core. This layout would drastically increase the overall chances of life existing there by allowing vital minerals to dissolve directly into the water. But regardless of what is happening in the ocean, sitting completely underneath Ganymede's ice and water is another truly surprising physical characteristic, an attribute that planetary scientists still do not have a definitive explanation for. Somehow, against all conventional geological rules, Ganymede is actively producing its own independent magnetic field. This unique magnetic field was first discovered by instruments in the year 1996, right when NASA's Galileo spacecraft began executing a series of targeted close flybys of the icy world. The single biggest indicator of an active magnetic field environment is the presence of bright, shimmering auroras, and incredibly, these spectacular auroras were detected glowing directly within Ganymede's thin atmosphere. Not only that, but as the Hubble Space Telescope studied Ganymede over an extended period of time, it became undeniably clear that these auroral bands did not wobble back and forth as much as scientists initially expected. This stability is likely the direct result of a phenomenon known as magnetic friction operating inside the salty subsurface ocean. An independent magnetic field is an incredibly significant feature because on Earth it acts as a protective shield that shelters the planet from deadly solar radiation, enabling complex life to flourish across the surface. Unfortunately, the field around Ganymede is not powerful enough to completely protect it from the harsh space environment. Because the Moon is tucked deeply within Jupiter's incredibly powerful magnetosphere and intense radiation belt, its surface is still continuously pelted with high doses of radiation. In fact, Ganymede's surface still receives about 5 to 8 rem of radiation daily, which is more than enough to make an unprotected human severely ill or cause death in just 2 short months. Even so, this radiation environment is still significantly better than what you find on its closer orbiting neighbour moon. Planetary scientists are still not entirely sure why this independent magnetic field is present here at all. Our own planet Earth possesses a powerful magnetic field because its central core is incredibly hot and molten, which allows active convection currents to constantly move electrons through the liquid metal, generating the global field that surrounds us. However, according to standard thermodynamic models, this exact process should not be happening inside Ganymede. Ganymede is significantly smaller than Earth, and given its modest size and material composition, scientists believe that its internal core should have cooled down completely by this point in solar system history, turning into a solid, inactive mass of rock and iron. A solid core would completely prevent electrons from moving through fluid convection, which should theoretically prevent any magnetic field from forming. Furthermore, none of the other major moons of Jupiter possess an independent magnetic field. In fact, Ganymede is the only moon in the entire solar system that has one. So, what exactly is going on deep inside this world? While scientists do not know the answer for certain, the ultimate explanation might lie directly within Ganymede's incredible gravitational relationship with its parent planet and its neighbouring companion moons, driven by a physical process known as tidal heating. Ganymede completes a full orbit around Jupiter roughly once every 7 Earth days, following a path that is slightly eccentric rather than perfectly circular. This means that at certain specific points along its orbital path, the Moon is physically closer to Jupiter than it is at other times. When a celestial object comes under the influence of a massive gravitational force, its physical body will naturally stretch and elongate in the direction of that force, as its internal mass is pulled toward the source of gravity. However, as the object moves further away from the source of gravity, the intensity of the pull drops, allowing the body to compress back into its original shape. Because Ganymede follows an eccentric orbit around Jupiter, it is constantly experiencing more and then less gravity, which forces its entire physical structure to continuously stretch and contract with every single orbit it completes. If you have ever taken a piece of blue tack or putty and pulled and stretched it repeatedly in your hands before rolling it back into a ball, you might have noticed that after a short while, the material becomes surprisingly warm to the touch. This heating occurs because the physical act of stretching creates internal friction as the molecules rub up against one another, and when this exact process is scaled up to the size of entire moons and planets, the resulting friction adds up to an incredible amount of energy. A tidal force that successfully generates internal heat through continuous physical friction is formally known as tidal heating. On top of that, through an orbital process that is absolutely fascinating to observe, Ganymede has formed a strict orbital resonance with two of its fellow Galilean satellites, Io and Europa, in what is mathematically designated as a Laplace resonance. For every single orbit that Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This mathematically precise configuration did not happen by random coincidence, but is clear, undeniable evidence of the Moon's mutual gravities continuously pulling on each other over eons, as the entire system attempts to conserve its resulting orbital momentum. However, this resonance means that Ganymede is constantly being tugged by its neighbour's gravities, putting its interior under an immense amount of gravitational stress. Therefore, it is highly possible that tidal heating is warming up the interior of Ganymede, just enough to keep its core in a liquid state after all these billions of years, allowing it to continue generating its unique magnetic field. Scientists do not know this for certain, but it would elegantly explain why the surface of Ganymede looks so incredibly interesting and complex. When you examine the surface of Ganymede, you will immediately notice that the terrain is split into large dark regions that cover about 1/3 of its total surface, and lighter regions that make up the remaining 2/3. By carefully counting the total number of impact craters present on these two distinct sections, planetary scientists can easily determine that the dark regions are actually much older than the lighter ones, as they contain a far higher concentration of craters. The lighter regions might feature fewer craters overall, but they are heavily dominated by long, continuous ridges and deep grooves that climb up to 700 meters in height and stretch for thousands of kilometers across the Moon. This terrain is truly an impressive sight to behold, but once again, scientists are not entirely sure how these massive ridges were originally formed. One leading explanation suggests that ancient tidal forces physically stretched out the crust of the Moon during a highly unstable, chaotic period of Ganymede's early history. Perhaps this same intense tidal force could have also warmed Ganymede's core and preserved its magnetic field to the present day. Whatever its true underlying cause, the magnetosphere of Ganymede has been absolutely instrumental in helping scientists understand the internal composition of the Moon. By carefully measuring the exact areas where the bright auroras appeared in Ganymede's atmosphere, scientists were able to mathematically confirm the existence of Ganymede's subsurface oceans, all without ever having to set foot on the world itself. As for the rest of Ganymede's deep mysteries, we may have to wait for the Jupiter Icy Moons Explorer, or JUICE, to find us the definitive answers. This advanced European Space Agency spacecraft is designed to investigate the inner workings of a number of Jupiter's moons, including Ganymede. Until that data arrives, we may have to let Ganymede's mysteries remain just that, a fascinating cosmic mystery. Now let us turn our attention to Callisto. Despite the undeniable fact that it stands as the 3rd largest moon in the entire solar system, I think the vast majority of people would be hard-pressed to state any real facts about it at all. This raises an interesting question. Is Callisto just a completely boring, inactive world, or do we simply not know very much about it yet? In reality, we actually know far more than you might initially assume, and when you look closer, it is far from boring. Let us start by looking at exactly where it fits into the wider layout of the Jovian system. Callisto is the second largest of the 4 Galilean moons, measuring an impressive 4,820 kilometers across, which makes it just slightly smaller than the planet Mercury. However, while its total physical diameter is only 58 kilometers less than Mercury's, it possesses only 1/3 of the planet's actual mass. This means that Callisto is significantly less dense, and its surface gravity is a lot weaker in comparison. It orbits Jupiter much further out than the other 3 Galilean moons, requiring roughly 17 Earth days to complete a single full trip at an average distance of about 1.9 million kilometers. Even at this massive distance, it is still completely tidally locked with Jupiter, meaning that the exact same side of Callisto always faces its parent planet. However, its distant location means that it is not locked in an orbital resonance with the other 3 inner moons, nor do astronomers believe that it ever experienced that kind of resonance in its past. Callisto possesses a very thin atmosphere composed primarily of carbon dioxide, and potentially oxygen as well, though molecular oxygen has never actually been directly detected by our instruments yet. We know for certain, however, that the atmosphere is so incredibly thin that the individual molecules contained within it do not even collide with each other, meaning that theoretically the entire atmosphere should be completely stripped away by natural space loss processes in just 4 short years. Because the atmosphere is still there. Scientists believe that Callisto's crust must be continuously replenishing the lost particles through the slow sublimation of carbon dioxide ice on the surface, a theory that is supported by some highly unique surface features. When you look at the surface of Callisto, you are looking at one of the single most ancient landscapes found anywhere in the entire solar system, with geological evidence placing its age at over 4 billion years old. You will immediately notice the distinct, speckled appearance of the world. Its surface is completely saturated with various sized impact craters, featuring a higher concentration of craters than any other object we have ever observed in space. In fact, the cratering is so dense that it has reached a state of physical saturation. Any new meteor impact that occurs today will likely just overlap and erase an older crater that was already sitting there. Outside of these constant meteor impacts, there is a total absence of internal geological activity on Callisto, meaning that cratering is perhaps the only major process that has altered the moon's physical appearance over its entire lifetime. Why exactly is Callisto's surface so incredibly old compared to a lot of the other large bodies in our solar system? Well, on geologically active worlds like Earth, there are a multitude of dynamic surface processes that can easily erase almost all evidence of past impacts over time. Earth actually features one of the least cratered surfaces in the solar system because so much activity happens on its crust. It experiences continuous weather, liquid water flow, plant growth, volcanic eruptions, tectonic plate movements, and human activity. All of these factors work together to continuously break apart, wear down, and completely renew the ground. Even other Jovian moons, like Europa or Io, have comparatively fewer craters thanks to the intense tidal forces that drive continuous geological renewal across their surfaces. This process simply does not happen on Callisto. Callisto shows absolutely no signs of internal geological processes, like volcanism or plate tectonics, and, as a direct result, its ancient surface has remained completely intact and untouched after all these billions of years. This complete lack of tidal forces and geological activity impacts Callisto in another highly unique way. There are no major mountains to speak of across its entire surface. When Callisto initially formed at the very beginning of the solar system, it was likely an active ocean world that has since frozen over completely, and apart from the continuous bombardment of meteors, it has stayed exactly the same ever since. Let us take a closer look at some of these massive craters, because the single largest examples are truly spectacular structures. First, there is Asgard, which stands as the second largest impact feature on Callisto, measuring a massive 1,100 kilometers in total diameter. Then, there is Valhalla, which holds the title of the largest multi-ring impact crater found anywhere in the entire solar system, boasting an absolute diameter of 3,800 kilometers. It is these specific multi-ring craters that give Callisto its incredibly unique appearance, as they contain far more concentric rings than craters found on other worlds. When these specific impacts occurred, the incoming space rocks were so massive that they likely punctured completely through the moon's thin crust, causing liquid or slushy material to well up and eventually freeze over again, creating the bright patches you can see right in the center of the impact zones. When you zoom in on these middle regions with high-resolution cameras, you will notice they feature a highly mottled appearance. There seems to be an incredibly stark contrast between the bright, elevated knobs and the darker plains that... Interestingly, these specific regional plains are a lot less cratered than the rest of Callisto's surface, which makes perfect sense if the floor truly represents a refrozen surface that sheeted over after the impact, likely making these areas up to 2 billion years younger than the rest of the moon. The massive concentric rings themselves are likely giant fractures in the crust, representing a structural failure in the brittle outer shell of the moon. Within these rings, those bright knobs remain highly visible to our probes. So, what exactly are these mysterious knobs? Geologists believe they are the degraded, eroded remains of the millions of ancient crater rims that once dominated Callisto's landscape. We do not know exactly why they have degraded so extensively over time, but it could be due to the continuous bombardment of micrometeors, or simply because the surface ice is slowly sublimating away into space over millions of years. They appear much brighter than the surrounding low plains, because the dark rocky debris left behind by meteors naturally falls down the sides of the knobs over time, leaving the pure, highly reflective water ice exposed right at the peak. The smaller impact craters on Callisto are also fascinating due to their structural uniqueness. Most impact craters on this world are significantly shallower compared to craters found on our own moon. For example, consider the massive structure known as the Lewin impact feature. This feature is well over 100 kilometers wide, yet it is only a mere 600 meters deep from the rim to the floor. This shallowness could be because the original impactor broke apart completely before striking the surface, causing more of a spread-out, shotgun-style effect across the terrain, or it could be that the surface has slowly leveled off over time due to the shockwaves of other larger impacts occurring nearby later in history. This specific crater is believed to be over 1 billion years old. Yet you can still clearly see the extensive lines of ejecta material that streamed away from the impact site, providing clear evidence of how incredibly unchanging this moon truly is. With certain other craters, like the Haar crater, there is even a large, distinct dome formation rising right out of the middle of the floor. With typical large impacts on other worlds, you normally see a few concentric rings and a sharp central peak rising in the middle, which is exactly what we see all over Earth's moon. However, Callisto features some remarkable examples of large craters where just the opposite happens. Look at the crater named Tinder, for instance. Instead of a central peak rising upward, there is actually a deep, hollow pit situated right in the center. Why exactly does Callisto possess such unique crater shapes? The answer could lie in the fact that Callisto's outer crust is not just brittle, but also remarkably thin, with soft, warm ice or a salty liquid ocean sitting directly underneath it. Current scientific estimates put the total thickness of the frozen crust at somewhere between 80 and 150 kilometers. The Galileo space probe, which spent several years orbiting within the system, dedicated a significant chunk of its mission to studying the Galilean moons. Galileo discovered that Jupiter's powerful magnetic field could not fully penetrate through Callisto, a vital clue that strongly implies there is a highly conductive liquid layer sitting just under the surface that is at least 10 kilometers thick. This specific electrical reading could not be generated by solid ice or silicate rock unless the ice layer is at least partially molten or exceptionally large temperature gradients are being maintained below the shell to create a conductive effect. Furthermore, gravity data suggests that Callisto possesses a small silicate core at its absolute center with a radius of about 600 kilometers. This naturally begs another fascinating question. Could Callisto be conducive to the development of life, just like the other icy worlds that harbour water mantles under their surfaces? Well, as we know, life requires liquid water and a reliable source of energy to exist. Callisto might indeed possess a massive ocean of liquid water under its crust, but because it sits roughly 800 million kilometers away from the Sun, it receives barely any thermal heat from our star. Furthermore, the complete absence of tidal forces removes the primary engine of internal heating, leaving the decay of radioactive elements within the rock as the only available source of heat to warm this subsurface ocean. Unfortunately, even visiting Callisto with a robotic probe would not easily prove if anything is living there. Moons like Europa and Enceladus possess active hydrothermal vents and geysers that eject water directly from their subsurface oceans out into open space, meaning we can easily investigate their habitability prospects by simply flying a probe through the plumes without ever having to land. No such active vents or geysers exist anywhere on Callisto, so scientists would have to physically drill completely through the massive ice crust in order to find out what is happening inside the water. When you combine all of these limiting factors together, planetary scientists unfortunately think that the environmental conditions necessary for life appear to be far less favourable on Callisto than on any of the other icy ocean worlds in the outer solar system. Nevertheless, Callisto should absolutely not be ignored or brushed aside, because if humanity ever decides to actively explore the outer solar system, Callisto would make the absolute perfect base of operations for human explorers. You see, orbiting at a safe distance of 1.9 million kilometers away from Jupiter means that Callisto is located completely beyond Jupiter's deadly main radiation belt. This makes its local environment thousands of times more conducive to human survival and long-term exploration than the harsh environments found on the inner moons like Io or Europa. Callisto also possesses a massive abundance of water ice on its surface that could easily be harvested and processed into liquid hydrogen and oxygen to produce rocket propellant, which is the exact staple needed to keep spaceships flying and human bases running. Separating the hydrogen from the oxygen also leaves plenty of pure oxygen for astronauts to breathe. Furthermore, the moon's absolute geological stability means that building permanent habitats and scientific structures on the surface would be relatively worry-free, without any fear of moonquakes or volcanic eruptions destroying the base. The complete lack of massive mountain ranges or deep trenches also means that it would be significantly faster, easier, and more efficient for astronauts to travel across the surface in rovers. Lifting off from Callisto would also be highly ideal, thanks to its relatively low surface gravity. And departing spacecraft could easily pick up a massive boost of energy by executing a gravity assist maneuver utilizing a close flyby of Jupiter. It is true that this is a highly futuristic prospect, but if humanity ever succeeds in becoming a true spacefaring species, this base is a distinct possibility. While Galileo did an admirable job studying Callisto during its mission, there are still a lot of information gaps that need to be filled, and with any luck, we will get those answers from the European Space Agency's JUICE missions soon. On the 5th of July in the year 2016, the Juno spacecraft successfully completed its long journey to the planet Jupiter and precisely inserted itself directly into a highly perpendicular polar orbit around the giant world. This milestone marked the beginning of an intense phase of exploration, meaning that Juno has spent a considerable amount of time over the last year gathering critical scientific data and capturing imagery around the single biggest planet in our entire solar system. Looking back at this monumental achievement, we must stop and ask ourselves what exactly this advanced robotic probe has actually managed to see out there, and whether it was truly worth all of the incredible logistical fuss, engineering effort, and immense financial cost required to get this highly sophisticated orbiter to Jupiter in the first place. If you have any doubts about the profound value of this mission, you simply need to take a close look at a few of these breathtaking, highly detailed pictures, and then you can honestly tell me your thoughts. Of course, it is vital to remember that Juno is far more than just a remarkably expensive camera floating through the cosmic dark. The spacecraft has been continuously performing several different, highly complex scientific experiments as well, utilizing an array of advanced instruments. The groundbreaking results of these diverse experiments have completely transformed and fundamentally changed the very way that modern planetary scientists understand the historical evolution of our solar system and the internal mechanics of Jupiter itself. So, what exactly has Juno been busy doing during its extended stay in the Jovian system? The probe follows a highly specialized, extreme path, moving in an orbit that brushes exceptionally close over the planet's cloud tops at its absolute closest approach, coming within a mere 4,200 kilometers of Jupiter's active upper atmosphere. On the opposite end of this elongated loop, the furthest point of the trajectory takes Juno out to a staggering distance of over 8.1 million kilometers away into deep space. Because the orbit is so incredibly stretched and elongated, each individual loop takes roughly 53 Earth days to complete from start to finish, and according to the original mission timeline, the spacecraft was scheduled to complete a total of 12 full orbits before reaching the scheduled end of its primary mission phase in July of 2018. At the specific moment this archival data was compiled, Juno had successfully executed what scientists call Perigove 6, which represents its sixth closest pass to the planet, meaning the spacecraft was sitting almost exactly halfway through its planned mission timeline. Because the robotic explorer has remained in remarkably good health despite the hostile space environment, mission managers have expressed great optimism that its operational lifespan could easily be extended far beyond the year 2018. One of the primary engineering reasons why Juno's orbit was designed to approach so incredibly close to the planet during its flybys is to intentionally avoid Jupiter's immensely powerful and utterly destructive radiation belt. There exists a narrow, relatively clear physical gap in space located precisely where the top of the planet's atmosphere ends and the inner boundary of the intense radiation belt begins. And Juno's flight path expertly exploits this tiny safety zone to protect its sensitive electronics. Before the spacecraft arrived, there was a massive amount of anxiety and concern among mission planners that Juno would still inevitably receive a devastating, fatal dose of radiation from the peripheral parts of the radiation belt that it must naturally pass through during its high-speed loops. However, when the initial telemetry came back, scientists were absolutely thrilled to discover that the actual radiation levels encountered in these specific zones were roughly 10 times lower than originally expected, which has been an extraordinary blessing for the long-term operational health and structural integrity of the probe's onboard instruments. To fully understand why this orbital design was such a crucial triumph, we only need to look back and remember the immense challenges faced by the previous dedicated Jupiter exploration probe, Galileo. The historic Galileo mission faced a devastating number of mechanical failures, system resets, and severe data collection setbacks due to the cumulative, unshielded damage its electronic components received from Jupiter's harsh radiation environment, primarily because its broader orbit forced it to travel directly through the absolute thickest, most intense sections of the radiation belt over an extended period of years. Consequently, modern mission planners were incredibly keen to do everything humanly possible to avoid a repeat of that tragic scenario with Juno. Another spectacular scientific advantage resulting from the tiny physical distance between Juno and Jupiter at its closest approach is that humanity has finally been able to see the surface features of the gas giant in completely unprecedented, crisp detail. The very first close-up images returned of Jupiter's mysterious poles, in particular, completely took people's breath away, completely shocking both the public and the scientific community. Some experts have even gone so far as to state that if you were to show these polar images to veteran planetary scientists without context, they would not even recognize what planet they were looking at, simply because absolutely no one expected the bizarre features that they saw. What you are actually looking at in these stunning polar views is a chaotic, tightly packed cluster of many massive cyclones swirling continuously around the South Pole. What makes this sight so remarkably striking is that the polar region of the planet looks completely different from the familiar patterns we are completely used to seeing on Jupiter, namely the iconic straight. Horizontal weather bands that dominate its mid-latitudes are entirely absent here. However, it is important to understand that the visual contrast of these raw public images has been heavily enhanced by processing software so that we can clearly see the intricate structural details of the clouds. To the natural human eye, the pole would actually appear significantly more muted, looking closer to a subtle, deep blue shade. This spectacular full pole image is also a complex mosaic assembled from a series of individual snapshots taken over time, carefully stitched together in order to show a fully illuminated daytime view across all sides of the planet at once. The North Pole, unfortunately, is not quite as clear or easy to observe in these image sets because that half of the planet was transitioning through its winter season during the flybys, meaning that large portions of the northern polar zone were shrouded in a deep, constant night. In addition to its powerful cameras, Juno also possesses the remarkable capability to peer incredibly deep into Jupiter's thick atmosphere by utilizing a specialized instrument known as a microwave radiometer, which was custom designed specifically for this unique spacecraft. By using this advanced radiometer to read the thermal radiation emitting from within the planet, scientists were finally able to map out and measure the exact concentration and distribution of ammonia gas hidden far beneath the upper cloud layers. What they absolutely did not expect to discover was a massive, highly concentrated band of ammonia stretching prominently around the planet's equator, with the ammonia gas highlighted in bright orange shades in the resulting data visualizations. This colossal vertical pillar of gas drops straight down from the upper cloud tops over a distance of 350 kilometers, plunging right to the absolute physical limit of what the microwave radiometer can see. Planetary scientists are deeply puzzled and thoroughly fascinated by this discovery because standard meteorological models of gas giants predicted an even, thoroughly blended distribution of ammonia throughout the entire body of the planet. They strongly believed that the intense convection currents and rapid rotation in the atmosphere would just naturally mix all the gases together uniformly over time, making this massive equatorial column an unexpected mystery. The discovery of this localized ammonia anomaly has forced researchers to completely re-evaluate their understanding of how heat, gases, and atmospheric fluids circulate within deep planetary environments. Outside of this strange equatorial zone, the data revealed that ammonia levels are actually surprisingly low in the surrounding areas, suggesting that some unknown, highly powerful dynamic process is actively stripping the gas from the upper latitudes and concentrating it right at the equator. This reveals that Jupiter's interior is not just a simple, well-blended pot of primordial gas, but a highly complex, layered, and deeply segregated weather system that operates on scales we can barely comprehend. Juno's microwave radiometer has essentially given us our very first look beneath the opaque veil of the outer clouds, proving that the structural layout of the planet becomes even weirder the deeper you descend. As Juno continues its multi-year journey around Jupiter, it is also providing an invaluable service by acting as a long-term monitor for the planet's long-lasting meteorological features, most notably the Great Red Spot. For centuries, humans have watched this monstrous storm from afar, marveling at its sheer scale and longevity. However, Viewing it from Earth, or even from telescopes in near-Earth orbit, can only tell us so much about its health and internal structure. Juno's regular, high-speed passes directly over the storm are allowing scientists to measure its gravitational signature and thermal output, providing clues about how deep the roots of the Great Red Spot actually go. The preliminary data suggests that this iconic storm is not just a superficial ripple in the upper clouds, but a deeply rooted monster that extends hundreds of kilometers down into the planet's mantle, drawing immense energy from the deep interior to sustain its furious winds. Furthermore, Juno's exploration of the Jovian system extends beyond the gas giant itself, as its wide orbit occasionally permits incredibly close encounters with the fascinating family of moons that call Jupiter home. In the latter phases of its extended mission, Juno has been systematically redirected to perform targeted, low-altitude flybys of these diverse satellites. These icy and volcanic worlds, each a unique laboratory of planetary evolution, are being viewed with the same advanced suite of infrared and ultraviolet sensors that Juno uses on Jupiter. By studying the moons up close, Juno is helping to bridge the gap between the historic discoveries of the old Galileo probe and the highly anticipated data that will eventually be collected by the next generation of dedicated outer solar system missions. Every scrap of data sent back across the hundreds of millions of kilometers of space brings us one step closer to solving the grand puzzles of our cosmic neighborhood. Beyond the mapping of atmospheric gases, Juno is also shedding light on the true nature of Jupiter's magnetic field, which is a key component in understanding how the planet originally formed. The magnetosphere of Jupiter is an absolute titan, stretching millions of kilometers into space and generating forces that can be felt all the way past the orbit of Saturn. Juno's onboard magnetometers are mapping this invisible shield with exquisite precision, revealing that the field is far more irregular and complex than previously believed. Instead of a smooth, uniform magnetic envelope resembling a standard bar magnet, Jupiter's magnetic field features localized hotspots and strange asymmetric distortions. This suggests that the internal dynamo driving the field, the churning ocean of liquid metallic hydrogen deep inside, is experiencing turbulent, localized flows that create an incredibly chaotic magnetic environment. This detailed magnetic mapping has profound implications for our understanding of the planet's core. For decades, a fierce debate has raged among planetary scientists regarding whether Jupiter possesses a solid, rocky core at its center, or if the intense heat and pressure have caused the core to slowly dissolve into the surrounding metallic hydrogen over billions of years. By carefully measuring the subtle gravitational tugs exerted on the Juno spacecraft as it sweeps past the planet, researchers are able to construct a highly accurate model of Jupiter's internal mass distribution. The emerging data points toward a fuzzy or dilute core, meaning that the central region of the planet is likely a vast, semi-fluid zone where rock, metal, and heavy elements are slowly mixing with the hydrogen mantle. This completely upends the traditional textbook view of Jupiter's interior and opens up exciting new questions about how giant planets grow and change over geological time. The implications of Juno's discoveries ripple outward, affecting how astronomers interpret the data coming from telescopes studying distant star systems. In recent decades, the discovery of thousands of exoplanets orbiting distant stars has revealed that gas giants like Jupiter are incredibly common throughout the universe. Many of these alien worlds are situated in orbits that bring them close to their host stars, exposing them to intense stellar radiation and thermal forces. By using Juno to develop a comprehensive, highly detailed understanding of our own solar system's largest gas giant, scientists are creating a vital baseline model that can be used to unlock the secrets of these far-flung alien worlds. Understanding the weather patterns, core structures, and magnetic behaviors of Jupiter allows us to make far more accurate predictions about the environments of worlds orbiting distant stars across the galaxy. As we reflect on the wealth of knowledge provided by this single robotic emissary, it becomes undeniably clear that the Juno mission has completely vindicated the immense effort required to launch it. The spacecraft has taken us beneath the beautiful, distracting facade of Jupiter's multicolored clouds and revealed a dynamic, puzzling, and awe-inspiring interior. From the geometric configurations of the polar cyclones to the mysterious equatorial ammonia towers and the fluid complexities of the core, Jupiter continues to challenge our scientific paradigms. The data collected by Juno will keep researchers busy for decades to come, ensuring that our understanding of the King of the Planets will continue to evolve long after the probe's historic mission finally comes to a close. Prior to the arrival of the Juno spacecraft, a significant number of planetary scientists had confidently predicted that the King of Planets possessed a completely solid, well-defined rocky core at its absolute center. However, when researchers began analyzing the highly precise data coming from the onboard gravity science instrument, the emerging picture turned out to be a whole lot hazier and considerably fuzzier than anyone in the astronomical community would have originally anticipated. This startling revelation could strongly imply that the central core is not a distinct, solid ball of heavy elements, but rather that it has slowly dissolved over billions of years, or perhaps a traditionally structured core doesn't even exist in the way we always thought. It is highly likely that it may be quite a long while yet until humanity manages to completely decipher and fully understand the absolute truth about this hidden internal structure, at least until all of the complex microwave, radio wave, and magnetic field data have been fully combined and meticulously cross-referenced to give us a far more complete and unified picture of the interior. Speaking of the planet's immensely powerful magnetic field, the definitive results collected from this specific investigation also came as an absolute and total surprise to the monitoring scientist. In several specific geographic locations across the giant planet, the local magnetic field strength turned out to be significantly more intense and powerful than they had mathematically expected, while in various other regions, the field strengths were notably weaker than predicted. These highly unusual fluctuating patches that you can clearly observe in the map data strongly imply that the massive magnetic field is actually being generated quite a bit higher up, well above the deep core of the planet, due to how remarkably irregular and uneven the field appears. This means the immense magnetic dynamo is perhaps originating directly within the churning, swirling layer of liquid metallic hydrogen that dominates the planet's vast interior. The planet's colossal magnetic field, as we know from basic physics, actively captures streaming space particles and channels them downward to create spectacular glowing auroras around the poles. To study this phenomenon up close, Juno comes fully equipped with a highly specialized infrared aurora mapper, giving us a breathtaking, deeply detailed view of Jupiter's polar light shows like we have absolutely never seen before in human history. In the central band of this stunning data animation, you are looking directly at the main auroral oval, and that brightly, rapidly moving point of light situated off to the left side is actually caused by the intense electromagnetic interaction with the closest of Jupiter's massive Galilean moons, Io. The long, luminous tail of light stretching out behind that moving point represents the lingering magnetic remnant of Io's rapid orbital motion through the planet's magnetosphere. Furthermore, the bright whites and vivid greens captured in this atmospheric image are the result of energetic iron ions striking directly into Jupiter's dense ionosphere from open space, while the deep reds are believed to be ions actively rising up from the planet itself. If this interpretation turns out to be entirely accurate, this marks the absolute first time this specific planetary phenomenon has ever been visibly observed anywhere in the universe. It is truly fascinating to realize that the vast majority of Juno's intensive data collection takes place during a highly compressed time frame, lasting for only a few brief hours per orbit as the spacecraft whizzes past at blistering speeds. Every single one of the advanced onboard instruments must work in perfect harmony to rapidly collect as much pristine data as physically possible during this incredibly short window of close approach, and this naturally includes the highly optimized imaging camera. This spectacular video sequence is actually a compressed time-lapse assembled from numerous individual frames, showing Jupiter rapidly approaching the northern hemisphere and then quickly receding away as the camera points back toward the southern hemisphere. This sprawling, singular image represents a masterfully stitched collection of all the individual frames that were utilized to construct that dynamic flyby video. As Juno makes its incredibly rapid approach toward the planet, you can clearly observe the chaotic, turbulent storm systems swirling violently around the North Pole, and then the viewing angle gradually shifts downward toward the lower mid-latitudes. When we meticulously zoom in on some of these breathtaking close-up shots, we can easily see the classic, elegant swirls and intricate weather patterns that we have all come to naturally expect from Jupiter's atmosphere. However, when you take a really close, careful look at the boundaries of these patterns, we can suddenly resolve these tiny, distinct white specks dotted across the landscape. These bright specks are actually extraordinarily high altitude water or ammonia ice clouds, which is proven by the distinct dark shadows that they cast on the cloud layers directly beneath them. They float significantly higher up in the atmosphere than the rest of the surrounding main cloud layer, and although they might appear quite small and insignificant from our distant vantage point, each of these specks is actually over 50 kilometers wide. Jupiter is just so mind-bogglingly huge that even a massive storm system looks like a tiny dot. Once you actually train your eyes to notice them the first time, you will honestly start to see these white cloud features everywhere across the planet. Due to the intensely freezing, sub-zero temperatures that constantly exist at this extreme altitude where these high-flying clouds reside, and because they are confirmed to be composed of solid water ice, it could very well be continuously snowing on Jupiter. It is truly remarkable to think that humanity is still actively learning so many fundamental new things about our giant cosmic neighbour. You might have easily thought that because Jupiter is the absolute closest and by far the largest gas giant to Earth, our modern space agencies would have developed a pretty flawless, near-perfect understanding of its internal mechanics. However, with the historic arrival of the Juno mission, it has become abundantly clear that we still have an immense amount left to learn. And there are probably still questions out there that we don't even know how to ask yet, let alone possess the answers to solve them. I honestly do not know where the time has gone, but it has now officially been over 3 full years since Juno first arrived in orbit around Jupiter. During this extended period of time, the robotic explorer has been continuously collecting incredibly valuable, deeply insightful scientific data about the absolute largest of our neighbouring worlds. The spacecraft has recently completed Perijove 21, which represents its 21st successful close polar orbit out of a grand total of 35 originally planned science orbits, meaning that the mission is now sitting well past its official halfway point. Some of the veteran viewers to this channel will undoubtedly remember the comprehensive video update I put together at the 1-year mark of the mission. But we must look at what spectacular things the probe has managed to discover since that time. As Juno continues its deep space journey, the massive collection of data it beams back across the solar system is providing an invaluable look at the deep structural layers hidden far beneath the visible exterior. One of the most significant aspects of this ongoing exploration is the long-term observation of Jupiter's dynamic wind profiles and deep atmospheric circulation. By measuring the subtle variations in the planet's gravitational field over multiple years, Juno has allowed scientists to calculate exactly how deep the planet's famous horizontal weather bands actually extend. The results have revealed that these powerful jet streams are not just superficial features skinning the top of the atmosphere, they plunge down to a staggering depth of roughly 3,000 kilometers. At that critical depth, the immense atmospheric pressure squeezes the hydrogen gas so tightly that it begins to transition into an electrically conducting fluid, allowing the planet's internal magnetic field to grab hold of the winds and force them to rotate uniformly with the rest of the planet's interior body. This discovery has completely revolutionized the field of planetary meteorology, as it provides the very first concrete measurement of the physical boundary between a gas giant's weather layer and its deep interior. Before Juno, scientists were locked in a fierce debate over whether the jet streams were shallow water weather phenomena or the outer expressions of deep planet-spanning convection cylinders. Now we know the truth lies somewhere in the middle, revealing an environment that is far more complex than any computer model had ever successfully predicted. The sheer scale of these deep-rooted winds is difficult to comprehend, carrying massive amounts of thermal energy from the hot interior out to the cold edges of space, driving the perpetual storms that define the visual face of Jupiter. In addition to mapping the deep winds, Juno's prolonged stay has allowed for unprecedented repeat observations of the Great Red Spot, giving scientists a front-row seat to the evolution of the largest storm in the solar system. Over the last few decades, astronomers using telescopes on Earth and in orbit noticed that this ancient crimson vortex appeared to be steadily shrinking in its horizontal dimensions. Juno's close-up gravity measurements and thermal infrared scans have added a vital third dimension to this data, revealing that while the storm is indeed getting smaller in width, its roots still extend deep into the planet's mantle, reaching down about 300 to 500 kilometers. This deep structural foundation explains why the storm has managed to persist for centuries despite the chaotic high-speed jet streams that constantly buffet its northern and southern edges. The Great Red Spot is effectively anchored into the deep, stable layers of the planet, drawing immense energy from the interior to maintain its furious, localized rotation. Beyond the boundaries of the gas giant itself, Juno's extended mission profile has increasingly focused on the diverse family of moons that orbit within Jupiter's massive gravitational domain. The spacecraft has executed highly targeted, low-altitude flybys of the icy worlds Europa and Ganymede, as well as the ultra-volcanic moon Io. By using its advanced suite of infrared and ultraviolet sensors during these brief encounters, Juno has captured high-resolution data that complements the historic discoveries made by the Galileo probe decades ago. These close passes are helping scientists map the surface ice distributions on Europa, track the shifts in Ganymede's unique internal magnetic field, and monitor the shifting volcanic hotspots on the surface of Io. Each moon represents a distinct laboratory of planetary evolution, and Juno's cross-disciplinary data is paving the way for the dedicated outer-planet missions scheduled to arrive in the coming decade. The wealth of ongoing discoveries sent back by Juno serves as a profound reminder of the value of sustained robotic exploration. Every single pass over the poles, every gravity map generated, and every infrared scan of a distant moon brings humanity closer to understanding the true history of our solar system. Jupiter stands as the ultimate template for the thousands of massive exoplanets we are continuously discovering around distant stars across the galaxy. By unlocking the deepest secrets of our own local giant, its deep winds, its fuzzy core, its irregular magnetic field, and its complex moons, Juno is providing the foundational knowledge required to interpret the characteristics of alien worlds throughout the cosmos. The journey is far from over, and the data collected by this remarkable spacecraft will undoubtedly continue to inspire and challenge planetary scientists for generations to come. As the mission progresses toward its final planned orbits, the engineering team continues to push the spacecraft to its absolute operational limits, carefully balancing the need for high-risk, close-up data against the degrading effects of the local radiation environment. Despite the intense bombardment of high-energy particles, Juno's heavily shielded electronics vault has performed magnificently, keeping the sensitive computer cores safe from corruption. This resilience has allowed the science teams to continuously refine their instruments and capture fleeting phenomena such as sudden atmospheric disruptions or newly erupting volcanic plumes on Io with astonishing clarity. The legacy of Juno is firmly secured as one of humanity's greatest triumphs in deep space exploration. A mission that looked beneath the beautiful, chaotic clouds of Jupiter and fundamentally rewrote our understanding of the solar system's largest world.